Okay, thank you all for coming in such large numbers. My name is Wouter van Ooijen. I teach informatics at the Hogeschool Utrecht in the Netherlands. And my main focus of interest is programming small microcontrollers, and especially in C++. And microcontrollers, those are the small things that are computers, but are inside some other device where you don't recognize them. I think I'm wearing one now. This will be one, and every watch will be one. There are a lot of examples. My favorite one is my son's dental brace, which has a small chip in it that records which times he wears it. It must be 23 hours out of 24 or something. And when he goes to the dentist, he reads it out and he shows him a nice graph. And he's very motivated to beat all the other guys who have a brace. But all these things contain a microcontroller some or the other. And you all know the bigger embedded systems. That's not what I'm talking about. There are embedded systems with big computers. They are almost like desktop systems. They have all freedom, all memory, all processing cycles. These are the really small ones. And when I talk about small, I mean this kind of specifications. This is a really small one, 256 bytes flash. That's not kilobytes or megabytes, it's bytes. And this is RAM, 16 bytes. You can do serious things with such a chip. But not C++, alas. There's no C++ compiler. It has a very crazy CPU architecture, and no one has apparently succeeded in porting GCC to that. But a little step upwards, it's only 2 or 3 times expensive. You have very small chips that Cortex M0 that do support C++, can very well be programmed in it. Oh, and there are also chips in this region that do support C++, but I don't use them. But these are the kind of things I'm talking about. Developing for this kind of chips is quite a bit different from developing for a desktop system. You have to very much care about CPU speed, the amount of code memory you have, the amount of data memory. And with a desktop system, you generally make an application for it, and you sell the application to your customer, and the customer pays for the hardware to run it on. These things are integrated in a product, and the vendor of the product pays for the chips. So, correctly or not, he is much more sensitive to the cost of the chips. Usually, if you exceed one of those parameters, you can buy a larger chip. That's immediately visible to the financial department. They'll start to complain. And things are paid for by the manufacturer. So, whether real or not, there's a real pressure on developers to squeeze their applications by code size, memory size, and especially these days by power they use. And most of these things are battery fed, so the longer you can run on a battery, the better. Typically, applications are small. Yeah, you can bet it. Large application won't fit. Volumes are high, so the extra price of hardware is felt very high by the manufacturer. When you program to a certain performance or timing constraint, you're mostly interested in the worst case performance, not in the average. Average doesn't count. Think of a car airbag. If you hit another car, you want the airbag to blow, I think, while your head is just starting to move. Not before your head starts to move, then you get first knocked unconscious by the airbag and then you break your nose on the steering wheel. Not too late, then you first break your nose and then you're knocked unconscious. Both things are not nice. Generally, such things have to do one task. They have to do it very well, very repeatable. There's no variation in it. It must be very dependable. In most cases, C is used for these kind of chips. I even know a guy who still programs in assembler and makes a very good living out of it. Of course, as everywhere, we should strive for code reuse. That makes programming cheaper. But in this application area, code reuse is very much hindered by a few factors. The small size of the code. The smaller your code is, the less possibility there is for reuse. The ones who write this code are often not programmers by education. They're electrical engineers. They know a lot about electricity and a little bit about programming. just enough to get things running, but not enough to make really good reusable abstractions. Well, they use C, so they don't have that much chance to make abstractions anyway. And every application, every time you program another of these gadgets that I showed, you have a somewhat unique situation. You have a different processor, different peripherals, some other different requirements. So at least it is felt that you must code everything out without reusing any other code. Maybe cut and paste reuse, that doesn't count. So reuse is not very, well, common. In my opinion, C++ should be used in this kind of contexts. It offers a lot of advantages over C, if only the better C parts, so you can avoid a few of the big problems in C just by using the compiler. You get for free a few other programming styles than the simple imperative C style, and those other styles give options for making reusable libraries in a better way than would be possible in C. Compared to working on a desktop, there are a few things that are different. Heap, in most cases, forget it. Are you going to squeeze a heap in, what is it, 16 bytes and the other one? Probably not. Floating point, well, these chips are very small, have integer-only CPUs. If you want to use floating point, you have to link in 8 kilobytes or so floating point library. Your performance gets divided by 10 or something, or 20 or whatever. Mostly don't want it. You go to the utmost to code only in integer or fixed point integers or something that masquerades as floating points, but not full floating point. Exceptions, debatable. You might use them. They cost some in performance, not that much. But exceptions are mostly not that of much of an advantage in such a situation. Exceptions deal in some flexible way with flexible circumstances. And these gadgets mostly have to work perfectly for one circumstance. And outside the normal circumstances, they can't work at all. They don't have the resources. So exceptions are not that, well, favorable. As a consequence, large parts of the standard library and other libraries written in CCC are unusable. If you don't have a heap, well, you can throw away a lot. And the difficult part is you don't know what part you have to throw away. And you only know after linking that the part library used requires the new operator. You don't have it. So redesign. The point of my talk is that object orientation at runtime is often not needed. We'll get more about that. And for the test case, I'll show you how to blink an LED on a microcontroller. That's the hello world for an embedded system. I don't even have a terminal to print hello world on, so it will blink. Okay, how would we do that in C? That's the benchmark for this field for C engineers. If it can do as good as that, throw it away. Don't consider it even. So here I have a main loop, and I set a certain pin high and low, and there's also some delays in it. And to set a pin high, I have to access the registers that are associated with that pin, and within that register, the address of the register is calculated there. I have to put a certain value at that address. And it all looks like a quite complicated operation, but it's not that complex. And when we see what the assembly code that's generated from this main loop, in red are the parts that are not important. We concentrate on the making a pin high and low, the interfacing with the hardware. You see only this is get the address. That's the whole thing that is calculated here. And here we must get the value -1 into that place. So we must construct that value -1, and you cannot do that. You cannot do that in one instruction. And here we have to put the value 0 on that place. 6 instructions in all. That's 12 bytes plus 4 bytes here. That's the absolute minimum. And all those important calculations that there were in this macro and the other macro, they have all disappeared because it's macros, expanded compile time, and at runtime it's just a constant. But macros, they have a lot of problems. Of course, they are efficient, and they generate efficient code, but you cannot easily build something else on such a macro. The user cannot easily augment it. I cannot make an alternative implementation of it and pass different implementations to my main loop. And, well, it's a macro. It has its own problems, scopes and expansion of parameters and things like that. So we can do better. C++ can do better. What would you do if you want to separate the hardware access from what you're actually doing with it? Make the pin high and low from that blinking for loop. Well, you make an interface class and derive a concrete class from that. You have an interface to set, give the boolean which determines whether it will be high and low. And for my chip, I use this chip, I have an implementation which provides that interface. Classic. Let's implement it. We have the interface. We have the same. It used to be a macro, but now it's a function that calculates the exact place in memory where we must put a value to make the pin high or low. And here we have the implementation of the class for the specific chip. You instantiate it with a certain port and pin. It saves those values, and in the set method, it calculates the value and puts its value there. Much more flexible. Now we could have different implementations and pass different implementations to our main loop to blink at different types of pins, or maybe the pin is remote over USB connection or some other fancy thing. We have decoupled what we do from how on which we do it. In the main loop, it would look like create an object, pass that object to the blink, and it will use the virtual method to make the pin high and low. Okay, nice, this is an abstraction. With an abstraction, you can build libraries on it. But there is a problem with it. If we now look at the code size, we had 16 bytes for the C version. Now we have 68 bytes for the C+ version. And that's only code. Additionally, we use 12 bytes of RAM. And making a pin high and then low again takes 65 CPU cycles, but used to be 9. This is not going to convince the guys who think that C is the best language for things like that. Why? What has gone wrong? Why does our nice abstraction take so much resources? Well, if we do this, this is what we do to blink the pin. We create the object, pass the object to the function, and the function calls the virtual method. What does that take to do? In our main, we must create the object, reserve some space on the stack, put those two values in it, initialize the virtual function table pointer. Then we have that object, and then we can pass the object to the blink function. That's in the main. That's already 18 bytes. In the function itself, it gets a reference to the pin it must blink, so it must dereference it to find the virtual function table pointer. That's here. Then it gets the correct offset to get the pin method, and it calls the pin method with 1 here. Here it jumps to that method, and this is the same again, but now for setting it to 0. The red ones are the same for, anyway, it's not what we're looking at now. We're now looking at making the pin high and low. 24 bytes. And of course, these calls here, they call the virtual method, and that's also quite a number of instructions because it must construct the address it wants to put the value to from these two numbers. This is constructed at runtime now. It's no longer a macro because here we have a constructor that saves only those two values. I could have pre-calculated those values and stored more pointers in it, but then I would have used more data. Maybe. But all in all, it takes quite a lot of resources just to virtualize the access to that one pin. In a realistic interface, we would have more methods for the pin. You must configure the pin for something and then say that it's an output and maybe switch it to an input again. That's more virtual methods. And virtual methods are not easily optimized away by the compiler, even if you don't use them. So in practice, it's even worse than this. Why? What happened? We just innocently applied a perfectly normal approach. But what we gained now is runtime polymorphism. At runtime, we can pass different pins to the same blink. Do we want that for a small embedded system? Well, in most cases, not. It's a chip, it's on a printed circuit board, it's soldered to its LED. You cannot easily connect it to another pin, you need a soldering iron for that. Well, if you can resolder your hardware, you might as well recompile your software. It's peanuts. So we gain something that we don't need for this kind of applications. And the fact that the actual action takes place here in the virtual method, and the caller, which is here, doesn't see what the implementation is. So the compiler is completely blocked from optimizing that away. He doesn't know what is called. But the flexibility that we have is nice. We can write code to Blink. I'll get back to the code. This code is nicely abstracted from how making high or making low is done. So that's something we would like to keep, but without this overhead. Okay, what is my idea for that? I can use static classes to make a compile time abstraction of what I want to do. A static class, a class with only static attributes and static methods, is a compile time only construct. Then I don't need a runtime object to do the operations on. If I want to parameterize such a construct, I can supply template parameters. And a class can be a template parameter, so I have the circle, I can parameterize the thing, it delivers a new class, and I can use it as parameter to another class. And it's all compile time only, so the compiler can see everything, can optimize away. There are no objects anymore, so no memory use, no RAM use. What's the principle? Instead of an interface class, I have a sort of prototype class. It's not really important what is here. It's just a reminder for me. This is important, this is a tag later for the template instantiation. Instead of a concrete implementation of the class, I have a template which can be parameterized by the same parameter that I would otherwise pass to the constructor. And it has a set method, which I can now write out because I know those values, and the compiler can see it too. And to direct later on the template instantiation, I say I inherit from this type, then it gets this tag that identifies it as an output pin. When I now want to blink, I have my blink function. It's templatized by that class. So I instantiate that class with the pin I want. This is the pin. Well, syntactically it's a class, but I think of it as a compile time object. So I have this pin compile time object. With it, I initialize the compile time blink, and then I call run on it, and it runs. Well, I omitted some details about initializing the pin and giving the pin a direction and how delays are done. That's all secondary. Okay, that was the code generated by the C version with macros. This is the code generated by the C++ version with this static class template approach. What's the same? The compiler has seen through all my abstractions and just generated the same code. But at source level, I can easily specify something else here, parse it, and then it will see through that abstraction. Completely same size of code, 0 RAM memory used at runtime, and same speed. Oh. I think that will appeal more to the C people. There are some ugly details to You see here, every time you're used to using a single dot, I have to use a double column, because these are attributes and methods, static methods of a class. And I have here a GPIO pin from that chip. Well, in practice, a GPIO pin is not an output pin, it's an input-output pin. So when I want to use it as an output pin, I must first configure it as such. But there are also pins who are also only output pins. And I don't want to bother my blinking function, it's grown into a class, with that detail. So when I get a GPIO pin as parameter, I transform it to an output pin. I want an output pin. Give me an output pin. And if you don't give me an output pin, I'll make one from it. So now when I initialize that pin, it will behave as an output pin, and I can set it high and low. Notice that I need explicit initialization. I don't have constructors anymore. There are no objects, so no constructors are called. That's a pity, I have to do it by hand. And this construct here, you can see it as sort of type narrowing. In case I get a pin that can do more than I want, a pin that it's an input and output pin, I narrow it down to a pin that can be only an output pin. The advantage is that my initialization here is complete for that purpose, and that I cannot inadvertently use a method here of that pin that I didn't want to use. It's like passing a type to a function, but a bit different. And the same happens here for timing. If I want to be completely decoupled from details, I must also pass to my blinking how I want to do timing. And it can be very different. On a very simple project, it can be busy waiting with a loop with knobs in it, but maybe it's a complete runtime scheduler with multiple threading and so. But this code doesn't need to know, it just waits. And even the representation of time might depend on what kind of timing abstraction I use. Because if I have a timer tick that's not a multiple of 1 millisecond, then it's not nice to have 1 millisecond as time resolution. So what dit actually is, that might depend on the exact implementation of the timing I use. I use four, I call them archetypes for pins. There's a pin that can only be an input pin, a pin that can only be an output pin, and a pin that can be both. They have no inheritance relation between them. There's not something that's capable of all things. These three are very different. An input pin you can use to get its value. An output pin you can use to set a value. An input-output pin you can also use to get and set a value, but you must first set a direction. That makes it different from the other two. That's why in the previous code I wanted such a pin, but in case I got this pin, I want to encapsulate it so that when I initialize it, it does init and sets it to output. Oh, and there's a last type of pin that's an open collector pin. That's very important in hardware for certain types of communication, I2C bus and things like that. And, well, it has its own peculiarities. When I get this kind of pin for my blinking, it will also use this pin. It's quite trivial. That concept of type narrowing is also nice. Here I have an alarm pin, and I assumed that the alarm was connected from the pin to the ground. So if they make a pin high, the alarm will sound or blink or whatever. But then there came some hardware engineer who turned it around. And, oh, sorry, I have the wrong thing. I have a pin, and I want to use this output, so I must first initialize it and set it to output. But if I convert it to a pin that is bound to behave as an output pin, then I can just initialize it, and it will be an output pin. And this also serves as an early type checking for the parameter template. If you supply it a type which can be used, let's say you try to blink an integer, it will give the error message here because it cannot instantiate it, and not somewhere deep down here. Yeah. To create one type of pin from another, it's classic use of templates. I have one basic template that is the fallback. If none of the specific templates match, it gets an error message at compile time. If one of the specific types match, and that's done via this subtype, which is available in the appropriate classes, then this will match. If it's an output pin, then this will match, and the methods are simply forwarded. If it's an open collector pin, same thing happens. Open collector pin behaves roughly as an output pin. And the interesting part is when it is an input-output pin, then the init must call the init of the underlying pin and set its directions to output. And it's all done by the compiler. There's no call overhead in it, it just gets expanded. This was what I said earlier. I have an alarm output, and I want the alarm to be active high. If I write true to it, I expect it to sound, but the hardware engineers did it otherwise. They connected between the output and the power supply, so it must make it low to give an alarm. That's bound to give problems in your code. So I have a const explorer which says that the active level is false, and I write not at active level initially, and then the active level when it must be made active. Well, that's ugly. I can just say that the alarm is the inversion of the pin. And now it behaves. False makes the alarm off, and true makes the alarm going on. And this interesting point is that this, no, look at the previous one, this has zero overhead. This set will go via the set here, where the value gets inverted, and deep down in the implementation it will be an if statement, and the else and if will be inverted, will be swapped, but it has no influence on the code size. This is free. And yeah, I think it's always better to say things in code than to say it in documentation, in the comment or documentation. This can get out of sync. And this good example of my favorite method, apply a decorator to something. And if you can apply a decorator to something, you can put decorators on top of each other if they have the same interface. And it is nice if it has zero overhead. This is the implementation of this invert template. Again, if it doesn't recognize what type of class it gets, it just gives a compile time error. If it has an input pin, it just calls the pin get from the underlying pin, inverts it, and returns that inverted result. For an output pin, it's just that you set the pin and then you set the inverted value. If you have an input and output pin, then you must supply both of these operations and, of course, forward the other operations. And for an open collector pin, no, it's the same as this one. You forward both, but invert the value get or invert the value you're writing. You can do a lot of more things with this kind of decorators. You can create, I showed you a pin in, I showed a pin out. You can create an input pin, you can create an open collector pin. You can create an open collector pin for an input-output pin by making low when it must be low, and by making it an input pin when it must be high. So when you use that, the library which uses an open collector pin, for instance, an I2C library, doesn't have to bother with the difference between an open collector pin and an input-output pin. I can create a kind of pin from another kind. I can also create a port. A port is a collection of pins. You can write a number of bits in one go, and create a port from a number of pins. Of course, there are more efficient ways to create a port. You can create a port by writing all the bits in one go to a specific part of hardware, if the pins are all part of the same port, if the actual hardware port, but this is much more flexible. You can invert things. You can write in one go to multiple pins or ports. If I have one pin, let's say that alarm pin that I had, and I want to write it, I can also write to a combination of pins, and one pin is the real hardware pin, and the other pin could be a logging. When I write to that pin, it logs on the debug interface, or it saves it to EEPROM for later inspection, or whatever. Then you have a T fitting that one operation goes to all others. You can make all other kind of nice abstractions this way. And the point is, again, if there is no inherent overhead needed in doing this, then there won't be any overhead. The compiler sees what it has to do and cuts through all the abstractions. It has some consequence in how you must program. Now the vehicle of abstraction is no longer a class with objects, but it's a static class template which is templatized to create the class which acts as object. The composition is by template instantiation, not by creating an object with a constructor, but by instantiating a new template with parameters. Your call syntax is class, call a method. And of course, it's templates. Everything is header only. There are no objects inside anywhere, although you could argue that what I create are compile time objects, but syntactically there are no objects. So you have no memory management problems. There can be no dangling references because dangling references are to an object that's no longer valid, and there are no objects anywhere. In fact, even when you create such a class locally within a method or within another class, it has global lifetime. It's created once. If two parts of your application create the same thing, you both want to invert a pin and use that pin inverted, then when you both create the inverted class, it is the same class automatically. So sharing of identical constructs is automatic. You must go to some pains if you don't want that. In some cases, you might not want it. You have, sadly, no automatic construction. You don't make objects, so there are no constructor calls. So you have to initialize each class you create explicitly. Of course, that initialization can cascade down to nested classes. So you only have to instantiate the top level things you use. And overhead can be zero. That is, using this system, your code can be as efficient as if you have written C specifically for this construct. Of course, if you use complex constructs, it will still be expensive, but it would have been expensive too if you coded it in another way. This was for I/O pins. I think I have found the correct abstraction for I/O pins. But to make truly reusable libraries for this kind of small hardware coupled processors, more abstractions would be needed. Let's take as an example, I want to write a library to read temperature from an LM75 temperature sensor chip. That chip uses an I2C interface. Well, what should be in my code? Well, I read, I think it's 2 bytes from a chip. I convert it to what's appropriate for my caller. And maybe I give him an error message if the bits don't appear to be a temperature. But what's more important is what should not be in my library. The details of the I/O pin handling. If I want to make pins high and low, I don't want to have those details in my code. I2C protocol. Maybe that protocol is implemented by bit banging. That's doing things by hand by some other library. Maybe it's a hardware module in my chip. Maybe it's something else. Maybe it's a remote sensor or something. I have to access it via some other protocol. Details of timing. In the I2C protocol, I have to make a pin high, then wait some time, make a pin low, wait again, make it high again. That waiting, the details of how that is done, or even if waiting is needed, should not be in this library part. That's timing, that's another part, must be independent. And maybe my processor is so slow that I don't need to wait at all. I can make a pin high, and then I can make it immediately low again, because enough time has elapsed already. It would be a pity if such a processor also had a call in there. Then the wait time would well, be tenfold or something. I also don't want to be bothered by how the data that I get from a chip is to be converted to what my user wants. If he wants floating point, okay. But if he doesn't want floating point, I don't want to be forced to include a floating point library for some step in the conversion process. And maybe he wants it in a specific unit, so he should be able to do that, but my code shouldn't be bothered with it. And especially if my code is used in a context where no conversion is needed, no fixed point is needed, then it should not be have the overhead of that. I even forgot error handling. It's another hairy one. So my ideal goal is to be able to write such a library without all those details. Those details must be template parameters that can be supplied by the user and can be very complex or very easy, and the library should scale to that. So what must I do for that? I have a good abstraction for points. I need a good expression for values, for timing, and that's a very large subject. It includes all multi-threading and synchronization that comes with it and everything like that. And of course you can say, take an existing library, but it must compile down to a few kilobytes at most. So it's, if it's simple. Error handling I have touched on. Parallel hierarchies is a difficult point. What I have told now is very fixed. It's fixed at compile time how the hierarchy of objects is related to each other. I have a pin, I invert it, then I combine it in a port, and then I do something with the ports. And all that is specified at compile time. Suppose I don't want to specify that compile time. I have some configuration file that gives me the hardware configuration. That should be possible with roughly the same syntax. Well, that's difficult to get it working. If only because you cannot have classes and templates with the same names. You have to come up with two different names or namespaces or whatever. That's ugly. Modern compilers are starting to do devirtualization. So you might say, well, if we have a perfectly devirtualizing compiler, shouldn't this approach be thrown away and rely on devirtualization? Well, maybe. There are a few pros and cons. One thing my approach has for it is that all the things are allocated statically, so you will know whether it fits in your chip at link time. And when you create objects at runtime, well, you will only know where it works at runtime when you're trying to run it. Well, that's definitely better. Of course, with real objects, you are much more flexible in where you allocate your objects. It can be a global stack or heap. And in effect, my approach has only global allocation. So you cannot reuse your memory when you have finished with one configuration, you want another configuration. Definitely a pro here. Of course, with real objects, you get the problem of naming references. And there can't be when there are no objects. This is an interesting asymmetry. Suppose I have, I told you when two parts of the program both make an inverter of a pin, those two are automatically the same when you use templates. You create the same class twice, so the linker collapses it to one. With runtime objects, you would have two different objects. Seems to be better in my approach. But now suppose that you make an abstraction that returns you one reading once when, let's say, a button is pressed. So effectively, you're differentiating the input. When it was 1, when it was 0 and now it's 1, you want to get a 1 once. If you do that with real objects, you can make 2 of those differentiators on the pin, and both will get a 1 when they read it. If you do it with my class approach, both parts of the program can make a differentiator, but it's the same. So only one of the 2 will get the 1, which is probably not what you expect. So the 2 approaches behave very differently in that way. That is essentially what this. Here you have no sharing by default, and here you have sharing by default. And in both cases, if you want it otherwise, you have to do some effort. And, well, of course, what I do has a very strange syntax and way of programming, so it's very unfamiliar. There are a few issues in C++ that make this approach a bit troublesome. I cannot make class templates and plain classes with the same name, so I can't have a template-like constructor thingy for my compile time classes and a normal class with a normal constructor. Oh, the syntax for static attributes gets horrible. It's filled with template and type name and all sorts of things. All the type name and template prefixes. And I feel a bit discriminated against. When you have virtual methods and you implement them in a concrete class, you can say override, and the compiler checks for you whether you really implement a virtual function, but it is not allowed for static methods. I don't know why. But it would be nice if I could also put override it and then be certain that I override something in the archetype class. So I really I'm doing what the archetype promised. Oh, that brings me to what I would like. You know, it's the December 5th now. In my country, Netherlands, we have the feast of Sinterklaas, where we get presents. So I have a few wishes on my Sinterklaas wish list. Could we please have override for static methods? It would be nice if the invoke operator could be a static method. It's not allowed. It has to be a real method. It would be very nice if templates and class could have the same name. And, well, these are less important. And I will not donate a kidney. Okay, to summarize what I've said. The standard practices and way of programming and the libraries that are used in C++ are often not optimal for very small systems. Hey, you're used to having plenty of memory, average performance is what counts, and that's not the case for small systems. It's a bit different there. The method I propose, I think, can be used to have the compile time abstraction power of class hierarchies without the runtime overhead. And in that way you can be efficient as efficient as C macros. So I think it could be a convincing argument for that community to switch to C++. But there's still a lot to do to make libraries around that. A simple thing, one of my students needed a string class. Well, of course you have std string, it's perfect, but it relies on the heap. So it's not usable on a small chip. And it's flexible, and you don't want that flexibility anyway in a small chip. And you want it to handle a string of a fixed length, and do that always, and within a fixed time. And not the flexibility of being able to allocate a larger part on the heap, with maybe some time performance. It's the wrong kind of good things. Okay, that was my talk. As usually, I'm much too fast. So I hope you have some good questions.
Starting with a simple question, what do I need to do this at home? And am I allowed to do this, or do you recommend to do this at home?
Well, you can Google objects no thanks. I have a small talk of it on some website, and there you find some code. I have the code for the I/O points, but I'm still working on the timing. And when you want to do interesting things, you need a timing too.
I need a device.
Oh, a device. Well, what I use is, what is this? Something like this. It's LPC114 NXP. You simply connect a serial port to it and you program it. I use GCC and then LPC21 ESP for downloading. It's all open source software.
So I guess one thing that was on your wish list, which came true, was the new using directive. So you can basically make a whole library of different chips and have your ports predefined for you. And all you do if you want to use a certain port on a certain chip is simply to use a using directive to get that particular library for the chip in.
I'm not sure that's what I want. Maybe you can use it, but what I do is include the correct header file and then instantiate the template from it. I must instantiate for a particular, I must instantiate the chip anyway because you must specify the clock frequency and a few other details. And then basically that chip class contains all the GPIO points that it has. So I don't really see the use case for that, but maybe.
If you want to blink more than one LED, don't you get horrible bloat code bloat?
What I shown was, let's say, a very small code in a template. If you have a situation where a large part of the code is replicated, then you need to use a non-template class and inherit from that. So you factor out your non-changing code. That's normal practice anyway. But in a lot of cases, the differences are very small, and the optimization effects by far outweigh the code load. So inlining eliminates nearly everything. But when you think that's not the case, of course, you must put parts out. Correct. That's always with template.
And one other thing I noticed when I switched from C to C++ is as soon as I have a global object with a constructor, C++ will have code for initialize those global objects, and that makes 50 bytes in code additional to the actual constructor. So
yeah,
there is another overhead that C++.
That's more than what I showed.
Yeah, exactly.
Yeah, I don't like global objects anyway because the initialization order is not defined over different compilation units. So,
but you also don't want to give, well, if everything is a compile time object, then you have no problems.
Correct.
But you definitely don't want to give pointers around to some objects because that is overhead as well. And especially if you are a little bit bigger and don't have only one object file, but if you have more than one object file.
Well, you can choose between two things. Compile time flexibility, and then you get almost no overhead. When you want runtime flexibility, you have to pass objects around. There's no way around that. So well, the choice is whether you want runtime flexibility.
No, the point is if I have global objects, I don't need to pass those objects around or pointers to those objects.
Yeah, true, but then what do you have the objects for? Then if you have global objects and the code uses those global objects directly, then the code is not reusable, that's not parameterizable. Then you have directly used it. It's not. What's the advantage in that over the, let's say, C approach?
Yeah, I have to look it up.
I have to think of it. You know where to find me.
Yes, so let's say I'm not using STL for any of those, I don't know, streams or any of these really slow and bulky parts. Let's say I would like to use some iterator but type traits. I'm assuming that it doesn't cost anything in runtime. But have you tried it to even, include something from the standard library? Will it like increase the whole image because when you include anything from STL, it will say, okay, now I have to like...
It's very different. And you cannot predict which part will do what. Okay, from a few STL abstractions, it will allocate on the heap. So it immediately needs new or malloc or whatever. But some other constructs don't. But the sad part is you don't know which
I know, but I was thinking if I use only the static stuff for type traits, let's say. Have you tried it? I mean, it works. It doesn't, increase the...
I did not use it, but I expect there would be no problem at all.
Okay.
But the difficult point is to know in advance which parts will...
Yeah, I mean, I'm assuming it won't allocate anything. I don't know, maybe it's strange to them. It's complete constructible, won't use heap, obviously.
Mostly for small systems, they say that runtime type information is a no. But in my experience, it has very little overhead. It gets a lot of overhead as soon as there's an exception somewhere. And I don't want exceptions anyway.
I see. Thank you.
I've been wondering about the virtual inheritance thing. If you use this implementation, except without the virtual function call, but use templates for that instead, wouldn't the compiler basically be able to optimize everything away? So, I mean, that you could still pass the port number and so on into the constructor as before, but the blink method would just be a template method with the pin class substitute as a template argument. And I think it seems to me that if the compiler can look at the whole code, it can basically just optimize this entire object away and generate the same code if everything.
Well, the point is whether the compiler for this code knows that it's this object.
If it's inline, I think.
If it knows, and it knows everything, then it could indeed optimize. It could optimize the same way as my approach, but yeah, it could. Maybe in 20 years, I don't know.
Well, okay. I would think that current compilers would actually do it. I mean, not in the case where you use virtual functions, but in the case where the blink method is templated with, or has a template parameter where you pass the pin class in.
You would put a template parameter here instead of here, and then have a virtual or non-funct virtual?
On the right side, I mean, the blink method or function. If it didn't take a base class parameter, but a template parameter, I guess the compiler could basically just inline everything and optimize.
But then what would you pass to it? Would you pass it those two numbers?
No, just the same as it's there. I mean, but all the code would stay the same, except that the blink function would be a template function.
Yeah, but what would be the template parameters?
Well, it would be implicit, or I mean, it would be the name that's there. So I mean, the compiler could either implicitly determine it, or you could write in brackets the actual port class.
I would have to think about it, but I'm afraid you would get the disadvantages of both approaches in that way. You would have to pass it as parameters, so it would be as template parameters, so it would be compile time flexibility only, but you would still have an object.
You would be blink open angle brackets, LPC 114 GPIO close angle brackets.
Yeah, but then you would pass those values as parameter, and I would want also be able to pass a decorated pin. That's a flexibility. If it was only this, if I/O pins were always of this type, then it would be very easy. But there are other types. I can have an I/O pin that's not on the chip itself, but on the other part of an I2C I/O extender. And I want to use those pins the same way.
Yeah, you probably wrap them in as like this, so that's the template without those arguments with a single type.
Yeah. I can abstract another chip, and it's, that abstraction requires the 2 pins for the I2C. It provides 16 more pins. And I can put those constructs on each other. I can have an I2C chip that drives another I2C chip, and there's a LED on the far chip. And that blinks with the same, well, it's not its code, but the template code. This code, well, the compiler knows, but the writer of the code never knows.
And did you consider maybe to change those compile time constants, like ones or zeros, with, I don't know, maybe type def empty structs, which will represent ones and zeros? For example, you can then choose the appropriate overload based on those types. In this case, you have dynamic. I mean, you have to create port and offset, for example, on a stack. And if you would have type deft compile time constants, you can just use overload resolution to pick appropriate overload and only to, and automatically to put port and offset variable in compile time. Still, you have port and offset on the stack at this point. So
I'm afraid I don't really follow it.
well, you could use overload resolution to overload on those compile time constants to have port and offset known in compile time.
Versions for this.
Yes, for example, for GPIO rec function, you can have multiple overloads which accept different types, and those types are just type defs for ones and zeros, and then you can automatically insert port and offset as a compile time constants, and not to have it on a stack.
But then you eliminate this calculation, you mean? Or
yes.
Well,
you can eliminate even.
But you would still
those.
have a runtime object for this.
What
do you pass to the blink? Do you pass a runtime object, which is polymorphic? Then it still needs a virtual method.
Yes,
that virtual mechanism hides the implementation from the compiler, unless it has whole program optimization, so it cannot optimize the things away.
Well, maybe not everything, but and at some point you could use, maybe if you have a lot of ones and zeros in as a constants, you can interchange them with type defs for empty structs and use the overload resolution to pick appropriate methods. I'm just talking about general mechanism, not maybe in this particular piece of code, but
maybe, but I don't see the advantage of it. Would it make shorter code or faster or whatever?
Well, it will not put, for example, some things on the stack which are compile time constants.
I think you would still have an object here, which is constructed.
Yes, object, but not the arguments.
Okay. Yeah, that could be. Yeah, but the real overhead is not in. Where I got it. This one. Sorry, very fast. The big problem, in my opinion, is between here. It is not so much this code, which is the code you're talking about. That's the implementation of the put and set, the set methods. But the fact that the compiler doesn't know that it is this code. If it knew, it could optimize most of it away. This is a virtual function call. This barrier prevents optimization.
Yes, okay.
And you are attempting to shorten this code. Okay, that's,
Good.
yeah.
Yes.
Let's say I decide to use a library and I build it and I look at assembly code and or the program doesn't fit on a chip anymore, or there are some unoptimized code which I thought will be optimized by a compiler, let's say. What should I do then? I mean, I wonder, so yeah, so we like go on a more high level, so C++ language. So we start to rely on some compiler optimizations. But let's say I get some high-level library like this one. I use it, so template-based library. And then my program doesn't fit on a chip, or it just, the compiler doesn't optimize. So now I need to make an effort to optimize the program, but this high-level approach probably will not allow me to do it. What should I do then?
You mean you have implemented your application this way?
Let's say. But for example, compiler did not optimize this function. So in C approach, what you can do, you can just modify your code, more or less. But here you just realize that someone else did it. So if something doesn't work, and I mean, if it's not a theoretical work, but you need to do something, then you have to dive into this library, or you just have to use, C, let's say.
The abstractions that I pass around are just classes with static members. There is nothing to prevent you from writing such a class by hand and putting a static member in it, which just the code coded out in the way you want. So the answer would be you can cut it in the middle and there start implementing it just like you would do in C. So it's not an all or nothing approach. But I would expect that in most cases, this approach would not generate worse code than a C approach. Otherwise, you're doing something strange. Maybe the higher level possibilities have lured you to doing something more complex than you would ever have dreamed of doing in C. That's possible. But then you have to do redesign anyway. Or you could buy a bigger chip, but convince your boss first.